And they concluded in the end that their best fit model was about 250 kilometers here, maybe 600 back here. The difference absorbed by internal deformation within Southeast Asia, and then dying out to maybe 40 kilometers here. So not really a link with the opening of the South China Sea. And in these models, the fault patterns are quite simplified. We tend to see them as single strands. But actually, when we look at these fault zones in detail, we find that there are multiple strands. Gravity here in the Tonle Sap basin area of Cambodia, we can see there's multiple basins related to it. We can map them out on from remote sensing data and see these fault strands. And I've been to many outcrops, and in the outcrops, in building sites, in quarries, very often you see strike slip faults. So they're very pervasive. We have difficulty dating the timing of them. We've got appetite fission track data that indicates uplift, focused around 33 to 20 something million years. It fits in with the general timing, but it would be nice to get more precise results for the timing of the deformation. So just up here, this is an example of a major strike slip fault coming through a quarry in metamorphic rocks. And these metamorphic rocks, some of these had ages as young as 32 million years. So this deformation post-dates some of the leucogranites in here that are 32 million years old. Regionally, we can map out strike slip faults, and they're very extensive, they're pervasive. Yes, there may be high displacement zones within these, but strike slip is extremely widespread. It's not these narrow zones. And often in close association with these, we get areas of hyperextension and metamorphic core complexes. You notice that this region in here, the Karat Plateau, didn't have so many strike slip faults in it. And this is the elastic thickness map. And one of the areas of high elastic thickness is the Karat Plateau. So this strong area in here has been avoided by the strike slip faults, and they wrap themselves around it, illustrating how these pre-existing fabrics influence things. We have started to date a few strike slip fault zones using calcite, uranium-lead dating of calcite. It's tricky, there's a lot of problems with the results, but for the Three Pagodas fault here, from these boudinaged features, we got ages of 44 million years and 23 million years. So there is hope that we will be able to understand the development of these strike slip fault zones in much better detail in the coming years. The Mei-Ping fault, which which we looked at just up here, it's dying out as we come to the south, and this study by Schmidt et al. 2019 very clearly shows that it transfers displacement into the Kulong Basin. And the timing of rifting in the Kulong Basin coincides with the time of left lateral motion on the Mei-Ping fault, and the timing of inversion in the Kulong Basin coincides with when it reverses to a dextral displacement. And we see this in this evolution here, where we have extension during the early stages here, and then inversion occurring in the later Oligocene here. This inversion is very important for the Back-Ho field and the production of that they have from the fractured granites. In Thailand, tracing the Maping Fault back, here we have a reasonable offset of structural belts along the Maping Fault here that suggests displacement could be up to 150 kilometers. So possibly 150 kilometers of displacement here, going to 20, 30 kilometers at the coast. So this model here by Ray Plumaz and Taponnier for the extrusion with this coming down to North Borneo just doesn't work. So the early view of escape tectonics was deformation in the northern half of Southeast Asia, largely driven by Indo-Eurasian escape tectonics. My view is deformation arises from complex interaction of plate boundary forces, some intraplate forces. And there is some form of escape tectonics, but it doesn't explain everything. Rigid fault blocks bounded by major strike slip faults, actually strike slip is extensive internally. Rift basins largely formed at releasing bends as pull aparts and extensional tips, no. Rift basins form in a variety of environments, including strike slip, but multi-phase extensional events, pre-existing faults. So if we just take a look at this, at a large scale, this study by Corti et al. Shows if we have a craton, strong, cold, rigid crust, a mobile belt, weaker crust, and we deform this. If there's a weak zone between these, we may have a very focused rift. If the mobile belt is weak, we may get a very distributed rift. And if the mobile belt is strong, then not as distributed, somewhere falling somewhere between these two models. And we have this situation in Southeast Asia with these continental blocks, the suture zones in between, and the Indochina block here. This dark blue color are the Cenozoic rift basins, Gulf of Thailand, Malay Basin, and we see that they're located over the mobile belt, the suture zone, and they're largely avoiding the continental areas. Looking at the boundary faults and just the dip of the boundary faults, some of them are very low angled. Some are, as you'd expect for normal faults, high angled. When we plot these in terms of west dipping and east dipping, we see a mixture of east and west dips in these high angle faults, but for the low angle faults, they're almost all east dipping. Why is that? Well, if we look at the suture zone, Sibu Masu here, Indochina here, the suture zone in here, this is the overriding plate. The Indocinian structural fabrics are mostly east dipping. And it's those low angle east dipping fabrics that are being followed by these Cenozoic structures. This is an example, these are down here examples of fault patterns that we see in some of the Thailand rift basins. And they're very complicated fault patterns. These are experimental models, analog models up here. For multi-phase extension. So how do we explain these geometries? In the past, they might have been explained as strike slip geometries, but actually these are a combination of pre-existing fabrics, stress rotation with time, spatial stress rotation, and also strike slip faulting. If we have a fault like this, how do we explain it? It's quite a commonly occurring fault pattern. You know, it could be horsetail at a strike-slip fault, but it could also be following pre-existing fabrics. Or it could be that the stresses have been locally rotated. Or it could be multi-phase extension, initially extension in this direction, then later extension in this direction. Coming back to this basin that we saw earlier in the Gulf of Thailand, most of the rifts trend north-south. So this trend here is probably following a pre-existing fault, a pre-existing fabric. And we see the basin's a mixture of this trend, but also there are some north-south trending faults. And if we analyze the displacement along this fault using seismic data and look at how it evolved, we've seen this section before. It started off by linking separate faults to form this fault zone. This is following the pre-existing fabric, these aren't. Then this gets abandoned, and there's a segment here that develops later that's following more the trend of these segments, and it's this that gives rise to this late fault here. So we have these complex fault patterns that get more complex as strain gets higher. We've looked at some pre-existing fabrics. Multi-phase rifting is a feature of parts of Southeast Asia. The Namkhon Song Basin is one example where there's early north-south and east-west fabrics. And then there's a pause in the rifting, and then this 16 to 10 million year age rifting phase, which is predominantly northeast, southwest. The extension direction is thought to be like this. But then it's influenced by these underlying fabrics too to produce a very complex fault pattern. We see this complexity in the North Malay Basin as well. Then at later times, after the rift basins have formed, we see inversion in a lot of these basins. In these green areas, we see inversion that gets particularly strong from about 15 million years up until the present. The Western Natuna Basin here is a particularly nice example of inversion of the Sin Rift half-graben geometries. So the region going into compression. But it's quite patchy. It's not ubiquitous. In central Thailand, there's no inversion. We get strong inversion in the Malay Basin. It's the main trap forming mechanism for the large fields in the Malay Basin, but not so in the Gulf of Thailand. And then as we go further north, we get an increasing number of inversion events and increasing intensity of inversion as we go to the north, and we see nice examples in the coal mines in the north. So getting to the summary part now. I put this together for hydrocarbon plays in Thailand, but this is applicable more regionally too. We've got this persistent subduction zone setting, and that's resulted in accretion of the crustal fragments that give rise to various pre-existing fabrics. We have rapidly evolving stress regime and hot, weak continental crust and lithosphere. And these feed through into the presence of low angle normal faults, basin inversion, diachronous basin timing, rapid post-rift subsidence, and the presence of faults in the post-rift section. And these in turn have positive and negative effects on traps or seal reservoir, or mixed effects in different parts of the basin. So overall, we see evolution from a dominance of extension to compression in Southeast Asia with time. And this coincides with the impingement of Australia on Southeast Asia. We have deformation of young, hot, highly heterogeneous crust composed of small accreted fragments. Evolution from large strike slip displacements to more distributed deformation with time in general. So there are elements of this model early that go to this model later. The upper crustal deformation patterns influenced by forces applied at the plate boundaries, traction related to mantle flow, intraplate effects, and local stress deflections. Basins are strongly influenced by pre-existing fabric stress deflections, stress rotations with time and the evolving stress regime. A little bit about Borneo. I've largely avoided arguing with Peter about this in this talk. I agree with him that the stratigraphic constraints he's developing are very important. And we need a revision of the old model for Borneo. And we are discussing this. The sticking points for me in abandoning the proto-South China Sea are that in Palawan, we've got Eocene age ophiolite. It requires an ocean to close in the late Eocene. There are also Cretaceous Eocene accretionary prism sedimentary rocks on Palawan and a Cretaceous ophiolite. So we need late Eocene seafloor spreading, and that gets very rapidly shut down by abduction after that. So unless the Keenan story is wrong, we have to deal with these events. Also, opening of the South China Sea and the anti-clockwise rotation of Borneo require loss of area in this region between the dangerous grounds and between Borneo. And I'd much rather do that through losing oceanic crust than to try and underthrust continental crust or have shortening. But conventional plate tectonics probably need modification, and there's a suggestion by Robert Hall, for example, that much of the later history of Sabah is one of uplift, possibly triggered by what's happening in the mantle, and deep-seated gravity sliding that's causing compressional features on the Sabah margin, as well as the shallower gravity-driven deformation related to the Neogene sedimentary basins. Okay, so I think these conclusions more or less repeat what I've just said, so I will leave my talk here, and thank you for your attention.
Okay, thank you, Chris. Very good presentation. So because of the time, so I ask Shivu Ran collect the question and also select some question ask you. Before they ask the question, I just discuss with you, because actually you are petroleum geologist. So I just want to discuss with you, because Southeast Asia, the basins, it's most of the basin is the tertiary basin. And yes. Also the oil and gas just find the tertiary basin. And most of the basin is lifting basin and back arc basin. So what about you? What about thinking about the Mesozoic basins? This is different. Mesozoic basins, it's different from the tertiary basin.
Oh yes.
I know, quite different, but why?
Very different.
Yeah.
And generally porosity is going to be the issue with the Mesozoic basins. They're the depth to them is going to be a problem, and the history will generally mean that those rocks are quite cemented. You know, PTT has explored in northeast Thailand, in Isan, in the Mesozoic basins, and older. There's Permian carbonates.
Okay.
To be that are the reservoir, and they do work in some places. In the Gulf of Thailand, you've got a small field, Nang Nuan, where the Permian produces because of karstification, and it's the same in Isan. Fracturing and diagenesis can result in porosity and permeability. Very hard to predict.
Yeah.
But it can do it. On the way down to the Permian, the Mesozoic has been drilled, the Karat group, plenty of sands, but drilling's really slow because they're so cemented.
Sure.
And there's tight gas sands in places. So maybe there's a sort of unconventional tight gas play, but again, very expensive, very difficult to make economic, I think.
Sure.
Yes. Other parts I'm just not so familiar with. But yeah, maybe if you've got Mesozoic carbonates, there's a chance, because diagenesis can always do something.
Yeah. Yes, we also trying to find some oil from the Mesozoic basins like South China Sea. And actually, we just found the east parts of the Indonesia, the Mesozoic from the Mesozoic, the just gas.
Yeah, I think in a marine setting, it's really difficult because the well costs are so high.
Yeah. Okay.
Yeah,
right.
In the Pisanulok Basin, there's a well that produced 1 million barrels from fractured Karat group.
Okay. Thank you.
Again, it's possible, but you can do it on land. You wouldn't do it in a marine environment.
Okay, thank you. Okay, Ryan, Shivu.
Okay.
Yeah,
okay.
Then you select the questions. You ask the Chris.
Yes. Yeah, Chris. There are questions from some audience, like Lenovo, like Hussein, like Sabine. I saw Sabine already, and I think you have a microphone, Sabine. You can directly use your microphone to ask a question to Chris.
Sure. Ni hao, everyone. Thank you so much for organizing this seminar. This is fantastic. And Chris, Sheshe, thank you for a really wonderful talk. My first comment is to say that I really appreciate and love your work, particularly that you resolve for us. We can't create or destroy sediments and crust and a lot of it without actually, thinking about the tectonics. So I really appreciate that. I guess I have a more...
You're fading out a bit there.
The Southwest... well, I've been perplexed by Borneo. I think that's something we can discuss more throughout the week and tomorrow. Is proposed to have docked kind of in the Cretaceous along the Billiton Depression. What's your view on that, and what evidence is there? Because I haven't actually in the public domain.
Yeah, I've got quite a history with Borneo. When I first came to Southeast Asia, I was in Brunei, and I made a decision very early on that I would look at the delta stuff. I'd look at overpressures, and I'd try and ignore as much as I could the geology of Sabah and Sarawak, because of the exposure, the amount of time it required to make progress with that. And so I was happy to hop on a plane and go to Thailand and look at the coal basins there. And then this year, PTT took over Murphy Oil, and now we have large amounts of acreage offshore Borneo and Sabah, and we're doing regional reviews and things, and I've had to get back into it, and I can no longer ignore it. And now I'm wishing I'd gone to all manner of places when I was living in Brunei that I never went. So I have lots of questions too. I think that early history is still really, really fraught. You know, it's not even resolved about Laconia, whether it collided in the Paleogene, whether it collided in the late Cretaceous. I guess I favor the late Cretaceous, but I think Robert Hall has it too early because there's still some Plutonism that goes on after 90 million years. So the collision would have to be more like 70 something million years, I think. I've also been looking recently with Bill Schmidt and Vietnamese colleagues at southern Vietnam, where there's a late Jurassic fold and thrust belt that ended deformation in the late Jurassic. I go, what's that doing there? What caused that? Something, so some collisional event or some change in the angle of the subducting slab caused that fold and thrust belt in the Ban Dong group in southern Vietnam. So I think there's a lot we don't understand about that margin in the subduction history.
Great. Well, we'll get to discuss more of it later this week. Thanks,
Yeah.
Chris.
Okay, Chris. The next question is from Lano about sheath food, and also this is a question about Professor Sun Zhen. Lano, are you there? And Professor Sun Zhen has something to say about the sheath food. Oh, his question is about sheath food. What type of structural environment can cause sheath food? Chris?
Okay, yeah. The only time a petroleum geologist would come across a sheath fold willingly would be as if he was looking at salt, which is highly ductile rock in the shallow subsurface and indeed at the surface. So if you've got a flowing salt glacier, you might expect to find sheath folds inside of it. They're a passive fold developed during ductile flow. So the implication is usually where you see it is in metamorphic rocks. You can find them in channel flow in subduction zones, for example. So it's a high strain environment. It implies ductile rocks that are hot and capable of flow.
Okay. And next question is from Sanzhong Li. He's a professor of China Ocean University. He also a structural geologist, and currently he works in the tectonic of South China Sea and work with CNOOC.
Okay.
Question. Professor Sanzhong Li.
Okay. Thanks, Professor Luan, to introduce my my situation. I'm from Ocean University of China and a structural geologist. And Chris gave us an excellent presentation for me. And I have 3 questions. In fact, it is difficult to put one basin as one typical basin type due to complex fault propagation, linkage, hard or soft, and jumping, something like that. So how to distinguish pull apart basin and transtensional basin or oblique extensional basin? This is the first question.
Yes, not easy at all.
Mm-hmm.
For a pull-apart basin, I would want to consistently see the appropriate strike slip geometries. You would want to have a fairly vertical fault that you could see jump in location at the right place, for the restraining bend to have the right angle, and so on. For oblique extension, you probably wouldn't see the very steeply dipping strike slip fault, principal strike slip faults, and they would all be 60-degree, 50-degree dipping faults. So you might have the same geometry with bends in it. If you looked at the displacement, is the high displacement zone one consistent for extensional faults, or is it consistent for strike slip faults? I think the displacement pattern along the faults would look different.
Sure. It's difficult. Okay, the second question is, your escape tectonic evolution is only based on or derived by the India-Eurasian collision system. How about the ridge subduction of Izanaki Pacific Ridge? If you read the paper written by Professor Miller, published in Science, you can find the Izanaki Pacific Ridge subducted under the East Asian continental margin in 55 million years. So this process, how to affect the basin formation in the East Asia or Southeast Asia. In fact, in 2012, the Vine model. In this model, I considered the dominant dynamics for the opening of the South China Sea is related to the subduction of the West Pacific, is related to the Izanaki Pacific Ridge. So what's your idea on the Eastern dynamic system?
Yeah. If you can be sure of the timing and you've got good evidence for it, then the slab window can have quite a significant effect on the tectonics at the time.
Yeah.
Oh, okay.
Yeah.
Okay.
Okay. Because of the time.
And Zhang Cunmei, she's
李老师，咱们就到这里了啊。
Okay.
Professor Zhu, I think one question from Sukhahala.
Hey, one more question? Last one. Okay, last one. Because of the time, it's
okay, just one more question.
Please.
Last one.
Okay, thank you. Hi, Chris. How are you?
Good, yeah.
Did you hear me?
Yeah, I can.
Yes, I have one question for you, Chris. Thank you for your nice presentation. So my question is about modern stress pattern that you explained before. Is there any relative to the earthquake pattern in the Thailand and the Southeast Asia? I mean, is there very relative?
Yeah, well, the earthquake data is used to define the stresses on the, particularly around the margins of the plate. Yeah, so that's built in. You've given me an opportunity to voice, if I can find, yes.
Yeah.
To suggest something here. We talked about long-term stresses. And in general, we think about, stress is being imposed on a region for millions of years. But a thought did strike me with the 2004 earthquake. We've got these post-rift faults sitting in the Gulf of Thailand, and they're actually very important for exploration. They're the small faults that trap a lot of gas, and they've been active during the Miocene to recent. But what are they doing there in the post-rift section? And when you look at the GPS data from the aftermath of the 2004 Sumatran earthquake, you see a lot of motion towards the trench, and the peninsula, Malaysia and Thailand moved considerably. But then when you go to Cambodia and the eastern side, of course, the motion was a lot less. Now, this is elastic motion, but I can't but help wonder, did that have an effect on the faults here? Is that what triggers these small faults in the Gulf? And here you're looking at, over 1 million years. If this thing happened every 500 years, we've got 2,000 events. That could be 1.4 kilometers extension in 1 million years. So maybe not all the deformation is related to long-term stress. Maybe some of it's, it doesn't matter what the regional stress looks like here long-term, it's these short effects that could be having an effect.
Okay.
Okay, thank you, Chris.
Okay.
Yeah.
Possibly a wild thought, but
Yeah.
Okay, thank you, Chris. Yeah, because of the time, I think a lot of questions still have, but because of the time, so I leave your address. I don't know, you have an email address, please? Leave your email address for the all of the today's meeting, and afterwards we can connect with you. We can discuss afterwards.
okay.
OK，秀文，你留一下他的地址给我们好吗
好嘞
？OK，Thank you, Chris.
，Thank you,
Thank you.
Thank you.
thank you.
See you tomorrow, Sabine.
Okay. Yes. See you tomorrow.
See you tomorrow. Bye bye.
You all take care.
Bye.
Yes, Sabine,
Bye.
tomorrow.
Thank you for the lecture.
Sorry, Hussein. Sorry.
No problem. No problem, sir. No
Sorry.
problem, sir.
Sorry. The audience who have questions.
No problem. No problem. No problem. The time's up. Time's up.
Bye
Thank
bye, Chris.
Bye bye.
Okay.
Thank you
Bye.
for the valuable lecture, sir.
Please.
See you
Fantastic.
tomorrow.
Thank you very much.
老师有关房间吗？
稍等一下。
哦，刚才那个孙真老师还有一个问题，但是时间确实是有点，问题很精彩的报告，然后。